Hi there and welcome back to the WhistlePig Classroom. Today we're going to talk about a really important topic, pitch stability in airplanes. In order to do that, we're going to have to talk about a bunch of things, so this may be broken up into a couple of pages and a couple of lectures. So let's start with the first concept. What is stability? Stability is the tendency to return to equilibrium. That's a lot of big words. What does that mean? Well, let's think about something simple. Consider a pendulum. Like if I'm hanging this pen from my fingers. That you can't see that, I'll draw a picture of a pendulum hanging from the ceiling. So here's my pendulum with a weight. And it wants to hang there. It doesn't want to go anywhere. If I push the pendulum over here and then let go of it, it will swing back. It may overswing, but it'll eventually end up back where it started. Now, on the other hand, I could take my pendulum, let's say instead of being on the string, it's a solid rod, like maybe I'm standing my pen up on the end. And if I push it, it'll fall down. This one is stable. This one is unstable. Why is this one stable? Well, when the pendulum is hanging, I'll draw a little bit bigger, off to one side, its weight is pulling down this way, but the rod, which is supporting it, is pulling up and sideways. And we know from Newton's second law, the sum of the forces is equal to the mass times the acceleration. The up force is countered by the weight, but the side force has no counter. So that means that the forces sideways are not zero. It's equal to the mass times the acceleration, so that means there's going to be an acceleration in this direction. Now, left to itself, it would go forever. Because there's air resistance and all that other stuff, it will eventually settle down and come to the center. Now, in our upside down pendulum, here it is off center, we have the same thing. Weight is acting this way. Since this is a solid rod that keeps it from just falling down, it has a force on it that is upwards and sidewards. But now you can see the sidewards force wants to push it over this way. So it won't ever come back to equilibrium. So, stable, unstable. Stable, unstable. Alright, so that's the basic concept of equilibrium. Now, what about an airplane? What about it needs to be in equilibrium? Well, when an airplane is flying along, it tends to remain at a constant angle of attack. And that's the important thing to airplanes, because all they care about is how they move through the air. They don't care where the ground is. They only care about how the lift forces act on it in relation to the forces due to gravity. So if we draw a picture of that, here's our airplane, and here's the center of gravity, which if you've looked on any WhistlePig gliders, you will notice has that marked on it. We have a front wing and a back wing. We have weight acting downwards. And each of these wings is going to produce some lift and some drag. We're going to ignore the drag for the moment, but that's what's going on. And because we drew the lift that way, we have to draw the velocity that way. Now, again, we have our usual sum of the forces. And in this case, we have the forward lift and the rear lift. Sorry, that's an L, not an F. It's got to be equal to the weight, because we're flying in level flight just like we've discussed before. And we're going to ignore the drag for a moment. Let's pretend that this is an airplane with some thrust, so the drag is canceled out. Alright, but what else is going on? To our angle of attack. We've also got a force acting around a lever arm. And as you know, if I apply a force around a lever, I get a rotation. So we can write that force times the lever arm, which is the length of the arm times the force causing it. Okay, and it turns out, I'm not going to prove this, but it turns out that you can write a similar law. The sum of all of these moments is equal to something called the moment of inertia times the angular acceleration. Basically, force is mass times acceleration. For the moment, we're not going to let the airplane accelerate. We're pretending the airplane is sitting there nice and stably. So by definition, that's 0. Now, again, this could be going around in a circle, but it also can be perfectly still. So what do we have to do to get this sum of the moments to be equal to 0? Well, what are the sum of the moments? We have the lift times front, and we're going to call this positive times L front, and this one is going the other way, so it's lift times rear times L rear is equal to 0. Okay, that's pretty cool. That says that this front torque or moment has to be equal and opposite to this back torque, otherwise the airplane is going to do this. But we also know that, standing a pen on its end, you can keep it, if you're really perfect, all the forces are 0. It just won't come back. This doesn't say anything about that. It just says, for the moment, at this particular instant, everything is fine. We're going to have to talk a little bit more about how lift is created and what its characteristics are in order to answer that question. So we're going to go ahead and take a break here, and then we'll come back and we'll do part 2. See you soon. Bye.